Greeting Earthlings! If you follow the channel, you know that we are resurrecting the Apollo communication system with the original spacecraft and NASA ground equipment. Over many episodes, we got voice going,
Apollo, this is Houston.
Then television, then the digital data uplink with its clunky paper tape test box, and we are now adding the digital downlink known in Apollo jargon as the PCM telemetry. In the last episode, we succeeded in connecting the Apollo guidance computer to the telemetry system. That is, an FPGA reproduction of the AGC, since the real one we had restored had been previously sold at auction. Nevertheless, our gate-exact replica should behave just like the original. And indeed, we could see that it was sending its own telemetry stream back to Earth. It's now time to try to receive that digital stream and attempt to decode it, so we can see what the hell the AGC is trying to tell us. If we do, we should be able to play Houston controller with the original toys. But before we get to turn knobs and connect wires, we need to brush up on the PM downlink, which we explained many episodes, or was that many moons ago. Voice and data from the spacecraft were transmitted back to Earth via one of three microwave links, the one called the PM downlink. The downlink carrier frequency was around 2.2875 GHz, more or less, as the exact value depended on the Doppler shift, which in turn depended on how fast the spacecraft was going. PM stood for phase modulation, the modulation technique used to modulate the information on that carrier. PM is a cousin to FM, the modulation format commonly used in FM radio. It is seldom used for analog communications these days, but it has the advantage of preserving the Doppler shift of the carrier. This is why it was chosen in Apollo, allowing the spacecraft speed to be measured from the carrier Doppler information. Voice and data were added to the downlink using subcarriers, a common radio multiplexing technique. As you can see on this chart, the complete modulation spectra of the Apollo comms was incredibly complex. Fortunately, we only need to worry about the downlink, where our data transmission is hiding. Here I have just left the microwave carrier center frequency highlighted. Voice was added on a subcarrier at 1.25 MHz, shown in green on the spectra. Similarly, data was added on a subcarrier at 1.024 MHz, shown in blue. The yellow stuff in the middle was a background of pseudo-random noise added for ranging that we won't get into here. Voice and data transmission used a nested modulation scheme. Let's start by explaining voice, which is simpler. Downlink communications is first established by sending the downlink carrier. For simplicity, we'll ignore the turned around ranging data, which looks like added noise, and show the clean carrier. The voice transmission begins with a pure 1.25 MHz sine wave, the green voice subcarrier we just highlighted in the spectra. That is then modulated with the voice from the astronauts using traditional FM modulation. On the spectrum analyzer, the resulting voice subcarrier appears fattened by the modulation. This signal is then added on the microwave carrier using PM modulation this time. A modulated subcarrier peak appears on either side of the main carrier. The final modulation scheme is then voice over FM over PM. To get our voice back, we just peel the onion in reverse order. For that, we'll need two receivers back to back. We first use our NASA microwave receiver, which is equipped with a PM demodulator. It says PM receiver right on it. You then feed the PM demodulated signal, which now consists of the subcarriers, to a traditional FM receiver tuned to 1.25 MHz. And voila, FM voice from the moon. At first we used my ham radio as the FM receiver. It worked great. We got it. See something?
Down voice.
Oh, that's via radio now. Okay. You can talk to me from the moon.
Hello from the moon.
Then back in episode 30, I breadboarded a PLL-based FM receiver to free up my ham radio. It worked equally well. I'm decoding. Talk to me.
Hello.
Yeah, that works. Alright, we have voice. But more recently, you might have spied a new instrument in the setup. Yes, I am now using a vintage HP8901A modulation analyzer instead of my ham or breadboard FM receiver. The HP unit is a metrology receiver, so it recovers voice just the same, with the added benefit of auto-tuning plus all kinds of advanced frequency, power, noise and modulation measurements. I did that in preparation to recovering data. The idea is that to switch over to data, all I'd have to do is select the other subcarrier from the NASA receiver and let the HP8901 auto-tune to 1.024 MHz and do the demodulation. However, there is a complication. If you look closely, these are not the correct data bits. That's because, unlike voice, data was not modulated using FM. Instead, it used PSK modulation. PSK stands for phase shift keying. Otherwise, the overall transmission scheme is very similar. You start with the 1.024 MHz subcarrier, you then add the PCM bits from the telemetry box. However, this time you use PSK instead of FM. You then add the resulting signal onto the microwave link using PM as before. The additional data subcarrier peak appears. The final modulation scheme for data is PCM over PSK over PM. Demodulation starts similarly, extracting the subcarriers with the NASA receiver. To switch to data, I tune the HP8901 to the 1.024 MHz subcarrier, but this time I can't use FM demodulation. So we have a bit of a snag because the 8901 does not support PSK demodulation explicitly. But it sort of kinda does implicitly because it supports analog PM demodulation. You see, PSK is simply a discrete version of analog phase modulation. It's just that in PSK, the phase jumps in discrete steps instead of varying progressively like in regular PM. In the Apollo case, the phase had just two values, 0 and 180 degrees, representing zeros and ones respectively, giving this weird-looking waveform with abrupt phase changes. Normally, you want a dedicated PSK decoder for this. But if we happen to feed this to an analog PM demodulator, like the one in the HP instrument, this would still generate a two-level signal. Granted, it will look analogish with that well-defined logic level nor fast transitions, but we should be able to whip them into digital shape afterwards. At least that was the idea. Practice turned out slightly different. Alright, so on the decoding, I've got good news and bad news. So right now, I am decoding voice. I am on 1.25 MHz. Say something, Mike?
1.25 megahertz.
Alright. Now I change it down here to 1.024 MHz. And got it. It got my bits, but they are decoded in FM, and what I want is phase modulation. And if I do phase modulation, I got some bits, but not everything I want. First, I need to make it really good on the low end, and then it's limited to 15 kilohertz, which is too slow for what I want to do. So here's a long bit, I get it, but the short bits is just too slow. It never gets there because I have this limitation on phase modulation on this instrument. So 51.2 bits per second is too fast for the 15 kilohertz max of this instrument, so I'm stuck there. Mike, turn me into low bit rate over there. Okay.
Coming up.
Low bit rate, I have the inverse problem, is that I am, yeah, so it's not going to do anything. I'm too slow. It's too slow for that machine, right? It starts to deform the zero. So I am squeezed both ways on that guy in phase modulation. Oh no, my brilliant HP receiver idea didn't work so well after all, at least not with that HP model. That's because although it can decode phase modulation and by extension PSK kinda sorta, this 1970s instrument is really meant for analog voice. The high bitrate is too fast for it and the low bitrate is too slow for it. Later instruments would do, but I don't have any, so there is no escape. I have to build a proper NASA PSK decoder. Hey, they did it in the 1960s with axes and bare skin, so I should be able to do that easily, right? It's meant for kind of narrow phase modulation.
Yeah, that makes sense.
And we are using DPSK, which is 180 flips like this, and it's a different demodulator that would implement for that. So I would have to make my own receiver. Okay, so I have to think about that one. A month of thinking later. Alright, so while Mike is figuring out the digital decoding of the bits, I am doing the hardware decoding. This would be the bits that the telemetry PCM is sending. I reproduced them with my little HP oscillator there. And the way they do it, they use BPSK, binary phase shift keying, which is a big word to just say that they change the phase of the signal every time the bit changes. So you can see how it's one phase and then bloop. Every time the bit changes, it switches phase. They just flip the signal and then they do it the other way around a little bit later. And the idea now is I have to make a demodulator to retrieve the bits. So let's do some proper BPSK demodulation. Here is our input signal at 1.024 MHz with the prominent 180 degree phase shifts. We call that signal A. Imagine for a second that we have a square wave signal handy with the proper frequency and phase. That's signal B, the reference signal. Now let's multiply the two. The first half period of the sine is multiplied by 1 volt, so it comes out unchanged negative. The next half period is multiplied by minus 1 volt, so it comes out inverted, also negative. The next portion of the signal occurs after a phase change. It is multiplied by 1 and comes out unchanged, positive. But the next portion is multiplied by minus 1, so it also comes out positive. In fact, you can easily convince yourself that all of the half periods will be flipped to positive until we hit the next phase change. At this point, the multiplication flips all the half periods to negative. You get the idea. In the 0 phase shift portions, everything is flipped to negative, and in the 180 phase portions, everything is flipped to positive. Now let's throw in a little bit of filtering to smooth out the spikes. Can you see our recovered bits already? We can easily clean them up to proper logic levels using a thresholding circuit. Here are our recovered bits. But the whole thing hinges on having a reference square wave that's phase aligned with our input signal. Turns out we can derive that from the input signal itself. We just need to perform a little more analog magic on the side. This time we square our input signal. Squaring it flips all the negative portions to positive, removing all the 180 degree phase shifts in the process. We end up with a regular waveform at twice the original frequency, while preserving the phase of our original signal. If we throw a PLL at it, we will clean it up further and get a reference at 2.048 MHz. We then divide it by 2 and we end up with the 1.024 MHz signal phase aligned, which we use for our reference signal B. Pretty neat! Today a student would do these computations digitally, throwing a computer and a few tens of billions of transistors at the problem. A modern hardware engineer would simply program them in a digital signal processing chip, also a few billion transistors. But the beauty of this scheme is that it could all be done in the 1960s in analog fashion with just a few tens of transistors. Mind you, you had to be a pretty darn good analog engineer to do it, not a hack like me. But as you will see just a couple years later, with the help of a few newfangled analog ICs from the 1970s, you could even do it without being an analog guru. Let me show you. It's actually a little bit more difficult than I thought it would be. But basically you get your BPSK at 1.024 MHz, and then the first thing that you need to do is recover the carrier, and for that you use a doubler, then you use a PLL loop to sync on it, then you divide it by 2, then once you have the carrier you multiply it by the BPSK signal, and you'll recover your bit after some filtering. And it's all made by a series of little circuits I have detailed here. So I want to retrieve the 1.24, but since the phase is varying all the time, it's not obvious how to do it until you realize that if you square this, you'll get a carriers at twice the frequency. And for that I use this little circuit over here, this little fellow, which is an MPY634. It's an analog multiplier. I feed it the signal on both of its inputs and it's going to give me the square out. So our squaring circuit uses this magic analog multiplier IC. It's part of the circuit here that I sketched in my notebook. I just read the spec sheet, added the few resistors, and voila, I have an analog multiplier that works at 2 MHz. All the difficult analog magic was done for me by the genius designer of the IC. And then I feed it to a little buffer amplifier, so we measure it at this red wire here. There you go, we have our multiplied signal, so there's a little bit of a hiccup when it gets through the phase shift, but altogether it's basically twice the frequency. And then the next step is to clean it up, and in order to clean it up I use a PLL, that's the 7046 circuit that we had used before to make the voice receiver. This PLL circuit is an old friend. That's the very one we had used in episode 30 to make the down voice FM decoder. It's a very good, very old circuit, still made today, but with a remarkably bad data sheet. Nevertheless, now that I have the hang of it from our previous project, I quickly got it to lock on the squared signal. Same thing, couple resistors and caps, and in the designer of the circuit we trust. And I measure the signal at the output, that's the green wire, so if I turn on green, there we go. So now I have a solid 2.048 MHz. So next step is to get the carrier back. This is just done by a divider by 2, and that's a 7474 flip-flop. A good old TTL chip from the 1960s. It's a 7474 flip-flop used to divide our square wave by 2. No need for any analog magic here. And now I want it divided by 2. There you go. So here's my carrier. Then it goes back into this circuit, which is another multiplier. This multiplier is the centerpiece of the decoder, used to multiply the BPSK signal with the recovered reference signal. We use the same analog multiplier IC as we had in the squarer. Well, we have one input of the multiplier. That should be, which one is that? That's our recovered carrier. The other input is our original signal, is the same as the yellow one. I'm going to multiply those two. Here is our multiplication result, and you can see our bits are coming back. When I do a multiplication one way, I get some negative result. When I do a multiplication the other way, I get the positive result. So we have recovered our bits from the beginning. Then we get to the next circuit, which is simply a comparator. The comparator is a lowly LM311, another friend from the 1960s, the king of comparators, which I wired as a Schmidt trigger. And there it is. We have decoded our bits. So I haven't tried it on the Apollo receiver still, but I should get a signal like this with much more noise. So we'll see how well this is controlled when I do noise. But I have recovered the bits that are encoded in the signal. I spent a little bit more time cleaning up my doubling signal. Turns out the PL is really noisy and messes up everything. And yes, of course, we were not immune to the usual analog shenanigans. the keen-eyed viewer will have spotted added parallel and series resonant filters at 2.048 MHz. These were necessary to filter out switching noise generated by the PLL, which was feeding back into the multiplier. Building RF circuits on breadboards is not the cleanest of solutions either. But I arrive at this pleasant result where you have the BPSK signal coming in. Here you have the double signal. Here you have the PLL divided by 2. You multiply this by that and put it through a comparator and you get your bit back. Awesome. And voila, it looks almost like in the theoretical presentation, all analog, no computer or DSP involved. However, from there on, I handed the bits over to Mike, who decoded the telemetry frame with his FPGA and computer. That part was of course also done digitally in Apollo with the giant and clunky computers of the time.
The following day.
Right, looks like we're receiving our first PCM bits
Yes.
through the air. So I put my contraption over here and I'm monitoring the bits and you're decoding the bits over here. Can you turn PCM on?
PCM.
Yeah, Apollo 13 with like data.
PCM.
And here we see it coming through. I have my bits in green. It's locked and you see stuff coming through.
Yep.
Yeah. And turn to low bit rate.
Great.
Okay, so now it's slowing down to a crawl. It's one line at a time. And I can see my bits here. I've slowed down a bit. So we had a few problems because it's not exactly the signal I expected. Yeah. So they obviously use some kind of low-speed electronics, and when they change the bits, I have a big AM component to it, right? It dips, the phase shift is right in the middle, and then it comes out with the other phase shift. And so that caused me problem at first because I would lose lock. I didn't expect that. It drops in the middle. It would lose lock. But we manage. And then you have now the AGC telemetry.
I do.
Don't
yeah.
you? You probably want to push it back to high bit rate because you don't get very much. All right.
So actually, let me start the AGC really fast. So what I have up is a recreation of MSK 672, which was the primary CMC monitor.
So this is a screen that they would have in the marker in the control room.
Yes.
We're going to do a little demo.
Yeah.
Right now, actually, your computer is turning dark. We have no data coming because the astronauts is not giving us telemetry. So can you please give us telemetry?
Yeah. Okay. So mode PCM.
All right. Ding. We are receiving the telemetry.
Yeah. This is MSK 672, which is CMC monitor 1. I copied it from this layout of the screen that we have.
That's an incredible amount of information.
It really is. Yeah. They have all the flag words, which is a ton of mode bits describing what's going on inside the computer, all your channel bits, which are your inputs and outputs, a lot of time information. You have the DSKY display right in the middle, a lot of information about resets and
But hold on,
channels.
DSKY display, there's nothing right now.
Yes, we're just in P00 right now, not ready.
Because it's exactly what the DSKY is saying.
Yep.
It has nothing on it.
Mm-hmm.
And all right, so if you run the program, then it's going to come alive.
Yeah. So I'm going to start program 61. This is Skylark, the Skylab flight software.
Okay.
And we're on a re-entry trajectory right now. So program 61 is going to start us getting ready for entry interface.
Okay, and then we should see.
Yeah, so you see P61 there.
There you go, and I heard the DSKY say something. Yeah, it came through. So we're reading remotely from the DSKY over here.
Yeah, so you
Program 61 flashing 1439, 15,000, something like that, and we have the same thing.
Yeah, the FL indicator right there means that the verb and noun should be
flashing, and it has the same numbers. It came down through telemetry. I see my bits coming here. We have it working.
Advance through the various screens here.
Okay, So okay, do you have more screens to go to, because I didn't capture that?
Oh yeah, there's a ton of screens.
Okay,
We're
go.
on a countdown right now.
So go. Okay, so let's see the countdown. So that would be easy to show here. Where is the countdown?
Should be in register 3.
Yeah, it's doing it. It's jumping 2 seconds at a time because.
Well, so is the disk is also jumping 2 seconds.
Oh, okay. High fidelity transmission.
The AGC telemetry for the most part is half a hertz. There are a few things that come down at 1 hertz, but it's mostly half a hertz. So we just transitioned to program 62.
Okay.
This 5025 is asking us to perform command module, service module separation.
Yeah, I see it. I see 5025, register 1 is 041.
Yeah. So I'm going to proceed and say that we separated from the service module. Keep going through screens here. Now we're running P63, which is going to actually start looking for 0.05 Gs to be registered on the accelerometers.
Okay. So it's amazing how much stuff they have. They are looking at from the innards of the AGC. What are all the ping numbers?
So as we transition between different programs in the computer, it switches between different subsets of telemetry that it sends down.
Okay.
So we're now in the entry and update down list, which is sent whenever you're in re-entry or whenever you're doing like a P27 update.
Okay, so they're just not sending those numbers.
Exactly, yeah.
All right, so then they would, so on your screen they appear pink, on their screen they didn't have color. You know what happened? They
I
just
think they probably
blank
just
them
would've
out or just ignore them?
Yeah, either stale numbers or they would have blanked them out, I'm not sure.
Okay. We have telemetry coming from the moon. So we have everything going. We have voice TV, telemetry, up, down. We're all set.
Yep.
We can go on vacation now.
It only took a few years.
Yes. All right.